So, dear colleagues, the title of my report was just announced. So, why is this topic? Well, rather a common accepted definition of intelligence is that intelligence is an ancient ability to efficiently achieve goals in a wide range of environments with insufficient knowledge and resources. And some researchers are focused on efficiency and probably insufficient knowledge and resources, while other researchers are focused on wide range of environments. And a wide range of environments causes universal methods because they can work in arbitrary computable environments, but these universal models are computationally infeasible, and their approximations are either inefficient or not universal. And focusing on efficiency gives us pragmatic methods which work in non-power environments, but which are probably more general than narrow methods, classical AI methods, but which are still intended to work in a highly restricted set of environments. So if we are really interested in general intelligence, which is both efficient and can work in as wide set of environments as possible, then we should somehow bridge this gap. And if we look at humans, then we can construct new efficient methods, and the AI field is what we are doing here. We construct narrow efficient methods. So probably universality or generality of intelligence is consists not in some universal method that solves all problems in a unified fashion, but probably it's a possibility to construct new narrow methods. And this is the main idea, and there is such concept as program specialization. We heard in keynote reports that there are a lot of specialized areas in the human brain, and we also heard that it would be better to construct some generalizations for speech processing, image processing, and so on, so, or for different kinds of memories. So probably there are some underlying general ideas, and we can consider specialization of universal methods. So we have some universal method which can be specialized to get all these specialized areas of specialized methods. And on the last AGI conference, there was a report by Alexey Potapov, which was entitled Metacomputations and Program-Based Knowledge Representation, but which was actually devoted to the application of the concept of program specialization to AGI. But this was a general idea, and right now no analysis has been performed which on concrete universal methods which could show us how to specialize specific universal methods to achieve some efficient pragmatic methods. And our current work is devoted to this problem. So let's briefly review what's the program specialization. If we have some program, for example, which has two parameters, then a specializer is such a program that transforms this program being given a fixed value of one parameter, and it constructs efficient projection of this program. So the result of specialization is a deep transformation of the program being given a fixed value of the parameter, and this projection can be much more efficient than simply calculating executing this program, this original program. And program specialization is widely studied in the field of interpretation and compilation of programs. There are well-known Futamura-Turchin projections. For example, if we specialize an interpreter of in some language and we specialize it with respect to some program, then we get a compiled program. And if we specialize in itself with respect to the given interpreter, then we will get a compiler. And there are really working specializers which can generate compilers from interpreters with, for example, twofold speedups. Okay, where we can apply this concept of program specialization in artificial general intelligence. We consider universal mass induction. It's of course not the whole intelligence, it's also only one part of it. Why we consider mass induction problem? Because if we consider efficient narrow methods which are applied in, for example, computer vision or machine learning, then these methods are applied independently to different data entities. For example, image recognition method is applied to one image, to another image, and so on, independently to different images. So this is a mass induction problem. And we cannot use universal induction in the mass induction settings because Kolmogorov complexity of a concatenation of different data entities which have mutual information will be much smaller than the sum of independent Kolmogorov complexities. So we cannot apply universal induction method independently to these entities. It will be non-efficient in terms of induction criterion such as Kolmogorov complexity. But we can construct such thing as a representation. And with respect to some representation, we can construct models of independent data entities, and we will be able to get approximate equality of Kolmogorov complexity of concatenations of these data entities and length of representation plus sum of Kolmogorov complexities of these data entities described within this representation. So we also heard a keynote report which was devoted to construction of representations, but not in a universal sense, but in a more narrow sense. So there was a class of representations described by deep networks. Okay, so in universal induction, we can search for models within some given representation, and we can search for the best representation for a mass induction program. And this can be done using derivation of Kolmogorov complexity, namely representational minimum description length principle. And it's easy to show that many practical methods can be considered as methods which optimize this representational minimum description length criteria, and it is shown. But also they not simply optimize this criterion, but they also efficiently optimize this criterion. And indeed, if some representation is not Turing complete, and here a representation can also be both Turing complete or not Turing complete. And if this representation is not Turing complete, then we can replace exclusive search with some more efficient search for model construction. Okay, so let me introduce two procedures in some universal mass induction. The first procedure will be M-search, which construct models of given data entities with respect to the given representation, and R-search, which searches for best representation given a set of data entities. Generally, we cannot do better than to perform exclusive search. But if we consider our M-search procedure is applied to different data entities with fixed representation. And if it is not Turing complete, then we can try to consider a specialization of M-search with respect to this representation. So here is it. Okay, and if we will be able to do it efficiently, then we will obtain a narrow, efficient method from a general one. We can try to perform direct specialization, but there are some problems. First of all, we have no general technique for exponential speedups. Only linear speedups are proven to be possible, and actually M-search is exponentially slow in general. And the second problem is that we don't have representations. We want to construct representations in practice. So our approach is to consider a simultaneous construction of representation and the result of specialization of M-search with respect to this representation. So if we consider the result of this specialization, we will get something with the following properties. It's semi-inverse to our original representation, and it should minimize this sum. So if S is a generative representation decoding, which transforms models back to data entities, then S prime is a descriptive representation or encoding which transforms data entities to models, and it cannot do more efficiently than exclusive search. Okay, we will refer to simultaneous search for SSM prime as SS prime search, and we performed some experiments in combinatory logic because we already have some engine for this. Well, because I have not enough time, I'll skip details. Mass induction in combinatory logic is a construction of some common representation and individual models, and application of this representation to these individual models will give us back our data streams. And in the case of SS prime search, we construct descriptive representation which directly constructs models from data entities. Okay, genetic programming for mass induction settings is also rather obvious, so I will skip the slide and go to experimental results. So we consider genetic programming in mass induction settings and combinatory logic on several examples. The first example is simple redundancy when all data entities are the same. And we find out that SS prime search found correct representation, and it's actually best representation. It should be noted that models and representations in our implementation cannot be empty. That's why models are not empty, have not zero, but length of 1. But our search found not optimal, but correct representation and correct model. And it's quite interesting why SS prime search could find the best possible representation and model, and our search couldn't. Then we tried our algorithms on purely compressible data. So here is the only redundancy is that the first bit is 0 and everything else is random. Our search completely failed, while SS prime search found the optimal solution. And it's quite clear why it happened, because our search should blindly pick out these random bits in a model, and it requires a very, very large search. But SS prime search didn't do this. It simply find S prime which cuts the first bit and then restores it back. So, okay, let's consider some more examples. Simple common regularity here. First 4 bits are the same as second 4. In this example, both S prime search and R search was equivalently successful. Because here was representation and models are of small complexity, so R search works in the settings, and the SS prime search also. Other examples here, first 3 symbols and second 3 symbols are mirror. And again here R search completely failed, while SS prime search found the correct solution. S prime descriptive representation, it simply cuts first 3 symbols, and S reconstructs them back in a mirror order. And the last example here, you can see that redundancy is that third and fourth symbols are the same. Again, R search completely failed, but SS prime search found the correct solution. Okay, so what we see? First of all, SS prime search constructs S prime, which is an efficient method for constructing models in this specific task. So if we give S prime, if we feed it with another example, it will extremely fastly construct a correct model. But in the case of universal induction, we will need to enumerate all the possible models to find a good one, even we are given correct generative representation. This is the obvious result. And the second result, which was slightly surprising, is that SS prime search is much more efficient in construction representations themselves. So this is the step for constructing representations in a universal settings. Of course, I think that there should be some examples in which R search will be more efficient than this prime search. I think that these are examples where data streams are independent and contain their own regularities, which are different for different data entities. But in general, SS prime search appeared to be much more efficient. Of course, it's not a total solution of universal induction problem, and it's only first step. And if we want to construct automatically such methods as deep learning, we need to consider specialization of universal induction with respect to limited classes of representations. And I think that this will be our future research direction. Thank you.